Welcome to the first seminar of the academic year. The seminar Ahilan is going to deliver today is part of a series of seminars in which we are inviting junior assistant professors that have recently joined the department to deliver a talk so that they can present themselves from a scientific point of view, and you, the department, can get to know what they have been doing in the past, and most importantly, what they plan to do, with the idea of fostering some collaborations, finding synergies, and so on and so forth. Ahilan just joined the department in September, so it's quite fresh, right? He's an aerospace engineer, bachelor and master, and PhD, educated in India, and then he moved to Kentucky University in the States, where he was a postdoc for 2 years, and now he has joined us as an assistant professor. He's mainly interested in very low Earth orbit orbiting satellites, in particular into hypersonics, gas surface interaction, and this is what he's going to be talking about today. So be patient. I'm trying to see if I finished.
Los siguientes eventos, eso, realiza, ¿no? De cosas que hay, futuras.
All right, that's cool. You have to stay here. You can probably use this to move, and stay here so that the micro is capturing your voice, also for those remote. Okay.
Okay.
Floor is yours.
Thank you, and thank you for waiting, and thanks for the introduction. I hope I didn't get stuck with another door. So, myself, Ahilan Appar. I recently joined here, and thanks for the opportunity to give the first talk of maybe this academic session or whatever. So, I'll be today talking in the general topic of whatever I did so far. To put them all together, I came up with this title, Multiscale and Multiphysics Modeling, from gas surface interaction to hypersonic reentry, and of course myself, Ahilan Appar. My academic story, I was born and brought up in southern India, Tamil Nadu, and I did my bachelor's from Madras Institute of Technology, where I started learning aerospace, and I thought I know everything. But when I went on to do master's and PhD at IIT Kanpur, the more and more you go into a research problem, you realize that you don't know a lot of things. And then I did my postdoc at University of Kentucky, where I looked at gas surface interaction at very low Earth orbits. So there I made peace with the fact that academia is like a never-ending learning process. And with that wisdom, I joined UC3M right now in front of you. And this is the overview of today's talk. So I tried to connect all the work together in a bigger picture, like a narrative. So there are two themes. The first theme will talk about gas surface interaction in orbital systems. Specifically, we'll look at what is very low Earth orbit and what are the advantages and challenges in it, and what are the scientific and technological development needs in those. And pretty much we are interested in how a satellite operates at those conditions. Okay, now let's say if I decommission that satellite and want to bring it back safely, then I also need to know how. So in the second theme, we'll look at what is a hypersonic reentry and what are the flow physics associated with reentry. And typically what I did was aerothermodynamic analysis, like try to couple a flow domain with thermal domain and see what happens. And also, when you couple two different domains at the interface, you are also interested in what happens at the gas surface interface. So this is the overview. And so theme one is pretty much from my postdoc work at University of Kentucky. And this work was done with the support from DARPA. And my collaborator and current collaborator and my postdoc advisor is Professor Savio Potingal. And this is a snapshot of all the active objects, include satellites and debris and everything, revolving in all of Earth orbits, right? And if we are particularly looking at low Earth orbit, I'm supposed to. Yeah. So this is like low Earth orbit where we have like 10,000 active satellites with 2,400 per year roughly, and all of them are moving at typically 9 to 14 kilometers per second. And if you look at the need for action, the emergency level is too high in low Earth orbits. So what does that mean? Ever since the first launch up until today, there are about like 35,000 objects revolving in the Earth orbit. And even if we stop, the further launches, the likelihood of more collisions, catastrophic collision happening in the orbits is continuously increasing. And we know, as a matter of fact, the launches are not going to stop. So there is an immediate need to clean the space, like of course space debris mitigation. In addition to that, also want to explore, since we very much depend on space technologies and satellites and everything, we need to also look at what could be a sustainable option or like an alternative option. And this is where the idea of very low Earth orbit comes into picture. And there are different, this is like a pretty recent concept, so there are different definitions of what could be very low Earth orbit altitude range. I find the definition from University of Manchester group who worked on Discoverer project of VLEO technologies, like the advancement of that. So, and this picture is also taken from their work. So this is how it goes. We know 100 kilometers is the Kármán line, pretty much like where your space begins. And so here on the y-axis I have altitude, and on the x I have density, and this purple line shows me is nothing but the incremental velocity. So the velocity the incremental velocity I need to impart to keep my vehicle or spacecraft or satellite in orbit, right? If we look at, for example, about 700 kilometer for a typical satellite, let's say, it would be about 1 meter per second, which is not much. And if we go little down, let's say about 450 kilometer, it is about somewhere like 50. And if we go further down, around 300 kilometer, it goes up to 1,000 meter per second, which is 1 kilometer per second, which is huge. So what happens is the effect of atmosphere is imparting drag on the vehicle. Thereby, we need to overcome that drag, so we need to give additional, propulsive requirements. So if we try to draw a drag threshold beyond which we have to consider the effect of drag, that would form somewhere around 450 kilometer, and between this altitude range, we define very low Earth orbit. Okay, all of those things that I just said looks like disadvantage, but why do we prefer that? Because operating at a very low altitude potentially gives a lot of benefits. That includes payload benefits. It improves Earth observational capabilities, and of course telecommunication performance and launch benefits. For the same launch cost or something, I can send more payload. And most important of all, I find interesting is the environmental benefit. So these altitudes are called self-cleaning altitude. Like because of the drag, the vehicle continuously experience drag and the orbit decays even if we don't do anything, right? So this here is it's a projected data for the next 100 years. This shows the density of objects which has size greater than 10 centimeter. If we look at the altitude corresponding to very low Earth orbit, we could see the density is very negligibly small because of the presence of drag, right? But whereas if we go little further, we could see, because of the absence of atmosphere, it is very difficult to bring back, like mitigate debris, and there's like accumulation of it. So with all of those, um, uh, yeah, like though we have all these benefits, there are certain disadvantages that, or I would say challenges. If we look at very low Earth orbit, and the major composition is of atomic oxygen, right? So we are looking at atomic oxygen that are interacting with spacecraft surfaces about hyperthermal velocity, which is about 5 electron volt or 7 kilometer per second roughly. So the major considerations are drag and the surface erosion because of the atomic oxygen, continuous exposure of your satellite to atomic oxygen. And for what I need to do is minimize drag by aerodynamic consideration like design and like modeling a better, choosing a better low drag material and things like that. And rest of the drag we need to compensate using propulsive requirements, right? And also these altitudes are these altitudes are rarefied atmosphere. By rarefied, what I mean is typically if I look at a flow, the particles will have some mean free path, like the average distance between two successive collisions. If we look at like VLEO or like for that matter outer space, the distance between two particles would be far apart, which is of the order or greater than the scale of the vehicle itself. So the probability of two particles colliding and equilibrium flow happening is rare. But what happens when an object moves through that? The gas surface interaction dominates. So typically, what I can say is gas surface dominates over gas collision. So in those situations, what happened? The continuum assumptions break down, and the CFD solver, which is based on the continuum assumption, all of this break down. And here we use something called particle methods. What does particle method say do? We just directly simulate the particles over the flow. So for this, to define the boundary, I need something called a boundary condition. Right? So I need to define how a gas particle interacts with the surface and scatter. So this atomic interaction of gas with surface macroscopically manifests as the drag experienced by the vehicle, right? So what is important is accurate modeling of this gas surface interaction. If I am interested in all the macroscopic like aerodynamic quantities like drag and all, drag and thrust performance, etc. And as we said, the dominant species is reactive atomic oxygen. And these are some of the common very low Earth orbit materials like aluminum, titanium, and you have silica coating, which is atomic oxygen resistant. And we have polymides like Kapton, which is like the golden layer, I guess, we see in a typical satellite image. So what we are interested in is how atomic oxygen interacts with various satellite materials. And in this particular problem, I'll come to that. But if we look at all the research ideas or like the major research areas in very low Earth orbit, like development of low drag or atomic oxygen resistant material, or to calculate my drag to know how much of the altitude and orbital decay is happening, or be it designing atmosphere breathing electric propulsion. So for example, instead of taking limited propellant like xenon, I would collect the atomic oxygen and then use it for propellants. This is something like a sustainable operation. And if we put together all these subsystems together, how does the system behaves as a whole? These are like major areas, but all of these boils down to the fundamental interaction of gas with the surface, right? So in this problem, or in this work, we are looking at atomic oxygen interaction with silica we started with silica for its atomic oxygen erosion resistance quality, right? So this is how the big picture looks. So we start with the material selection, which is silica. Then we model it in molecular dynamics. Like we basically create a small surface element, surface of the silica. Then we try to impart or like shoot the atomic oxygen onto the surface, which is corresponding to all the orbital conditions, like the velocity equivalent to your vehicles, and that is the velocity the atom interacts. The big picture is that we are studying gas surface interaction of atomic oxygen with silica surface using molecular dynamics. After that, from that, I'm going to build a gas surface interaction model, which is like a boundary condition, which is rich in atomic details, or I would say like the molecular fidelity. These boundary conditions can be used in particle solvers like DSMC, PIC, etc. Now, so the surface preparation starts with a unit silica cell, and then I replicate it in all three directions to create a crystalline cell, crystalline substrate. But the realistic amorphous silica is not a crystal, so we need to thermally anneal it. By that, I mean I heat it to a high temperature and then I cool it. So there are different ensembles in my molecular dynamics, like the way you treat your system. Where there are some of them are NVE, NVT, and NPT, which means number of particles, V is volume, T is temperature, P is pressure, right? So we basically treat using NVE, NVT, which is pretty much like number of particles, volume constant, and temperature can vary. It is like you are adding some thermostat to your substrate, right? And then the same for NPT. By doing that, I get an amorphous silica, which is close to a real silica, kind of. Now, I'm interested in, if we look, before we used periodic boundary in all three directions, which means it's an infinite, like infinite substance, right? But we are interested in gas surface interaction, so I need to prepare a surface. So what I'm going to do is create a vacuum in the z direction, which is where I'm going to shoot my atomic oxygen. So by creating a vacuum, it is like slicing the infinite crystal. So there will be like deformed bonds and things that forms a surface. And we just equilibrate it with the temperature that I want my substrate to be. So this marks the end of substrate preparation. At this point, we validate the structural properties of silica with both experiments and molecular dynamics using different interatomic potential. And I forgot to mention that in this problem, we used reactive force field, which is preferable for calculating chemical reactions on the go, and for scattering simulation, that's why we preferred reactive. So this is how a typical simulation looks. So we shoot atom at a certain distance above the surface, so that the van der Waal effects are negligible. Then it hit the surface with velocity equivalent to your satellite velocity, right? And it scatters. So this is one such scattering like that to improve the statistical convergence. We performed like 20,000 independent simulations like that using molecular dynamics package Lamps, and out of which 23% of particles reflected, right? And the remaining 76%, they are absorbed to the surface, and that's a problem for later, but right now we are focused on the particle that is scattering off a surface. Now, so what we are basically do is try to take all this independent scattering, and once the particle reflects, collect the post-reflected velocity and try to see how the distributions look, right? Which is what we get from a molecular beam experiments, where they actually shoot a beam of atomic oxygen onto the surface of interest, and the beam scatters, and then they collect the post-scattered beam and try to see the distributions. And in this work, Professor Minton at University of Colorado is a collaborator who does the validation effort for different materials. And in this particular case, we try to validate with a material called BSF30, which is a polymer that has silicon in it, which means it's not actually a silica layer, but a material that has silicon in it, which upon exposure to atomic oxygen forms a layer of atomic oxygen resistant layer of silica, right? So that shows that we can also use material that oxidize to form silica on top, which prevents the material from further damage, right? And so on the left side, we have, for example, if I shoot a number of atoms at 60-degree incident angle, they reflect somewhere around 60. The reflection is most probable centered around the 65, and it produces a broader distribution, which agrees well with the experimental result. And here, this shows the directional energy transfer, which means, for example, at a particular direction, a particle reflected, but reflected with how much energy, right? So we try to put the energy and the direction together, and that looks something like this. So the idea is it agrees very well with the molecular dynamics, the beam experiment. And on this side, so after validating this, I try to do something by superimposing the 2D contour of energy contour on top of the scattering data. So it is like you can see all the particle that's scattered has a reflected energy that is lower than the incident energy, which means all the collisions are inelastic. So the particle, upon hitting the surface, imparts some of the energy and reflect, right? Now we come to the part where we develop a new model. Before that, the new model is called diffusive Cercignani Lampis slot model, DCLL. But before that, let's compare how the classic models like Maxwell and CLL compares with the beam experiment. Maxwell, of course, it's fully diffusive, so the probability of reflection is equally probable in all directions. So you get a nice circular distribution. In reality, I guess CLL was introduced to capture this partial scattering behavior in like a lobular distribution, but even CLL cannot capture the distribution behavior that we observe in typical orbital conditions, right? So this model that we proposed, it is kind of combined best of both worlds. That's why we named it as diffusive CLL, which gets its scaling up parameters from the post-reflection data we obtained from the molecular dynamics. And this is how it looks. So we were able to capture this reflection, post-reflection behavior, or like the influx in-plane angular distribution perfectly, or to very good accuracy. So the good thing is, there are other GSI models which are physical, but implementing them into particle solver framework is the challenging task, right? So my model as a standalone model can produce better results, but I want to fit that into a boundary condition and see how the macroscopic flow properties are behaving, right? So this DCLL model pretty much has the same implementation procedure like CLL and diffusive, and so it directly fits into the DSMC framework or PIC, which is like a future extension. And also the beauty is that it includes the material specific interaction. For example, this particular scattering behavior is for a silica substance, right? If I use a different material, then based on so we have something called the model interaction parameters that would capture the material specific data into it. So with that, I'll this part, the theme 1 is concluded. With the future work, we try to include this DCLL model for different angle of attack and various surface temperature, which will result in a lookup table that can be easily integrated, like a library form that can be integrated in the DCLL gas surface interaction model in the particle framework. And also, I'm interested in looking at what happens to a surface when we expose it to atomic oxygen for a longer time, right? Even in this model, for example, if I try to expose my silica surface, I mean, like exposing to an actual longer duration is not possible. So with certain interval of time, we try to, shoot the atomic oxygen onto the surface to let it reach a saturation state. I could see the graph reach a saturation state. And now I want to do the same scattering and see what happens. So this is and also build a GSI model. This is a work in progress. And possibly extend this DCLL model to other materials. For example, highly oriented polypyrolytic graphite, which is called HOPG. In a beam experiment, which was done to study the gas concentrator's shape in very low Earth orbit or low Earth orbit conditions, they try to compare the scattering behavior of, let's say if I use silica on the concentrator and if I use HOPG on the concentrator, how does the collection efficiency and all these things compare? And like HOPG, the beam experiment shows this surface produce superspecular behavior, which is more desirable for if I'm interested in low drag, right? So the possible extension of this work is to look at model HOPG in molecular dynamics and do the scattering experiment and try to build a model or like the model interaction parameter that can be used in the existing DCLL model and try to do a system scale simulation, right? And this is a bonus slide where we actually try to apply that GSI as boundary condition into an open source solver, Sparta. But these results are not exact because it was still in the developmental stage. I just wanted to show that scale bridging is possible if we have an accurate GSI model, right? So for example, this is specular behavior and diffusive behavior, and the realistic behavior is somewhere in between. So this is the bigger picture of it. And with that, we come to the second theme, which is hypersonic reentry, aerothermodynamics. Probably the boring part of this lecture, I guess, because I lost my touch. Yeah, I mean, this work was done from the grants from DRDO and ISRO. And my advisor is Professor Rakesh Kumar at IIT Kanpur. So this is how a typical reentry looks. A reentry begins at 100-kilometer Kármán line. And then based on my mission requirements, I can take a steeper path or narrow path. But let's say this is my vehicle and it's going to take a certain path. What happens is the vehicle that enters with a very huge kinetic energy due to air friction, there will be conversion to thermal energy and a lot of heat. And we could reach a maximum heat flux of about 100 to 10,000 kilowatt per meter square at semi-rarefied regime. Semi-rarefied regime is like somewhere in between like your rarefied and your continuum regime, somewhere here. And still the velocity of the vehicle is in hypersonic regime, right? So at this velocity, we have all kind of complex phenomena happening. For example, ionized gas try to cover the communication devices and block certain radio frequency waves, which is called communication blackout problem. And so typically, the vehicle will experience high temperature gas, which are in thermal and chemical non-equilibrium. And that makes reentry a multiphysics and multi-length scale problem. So in a typical reentry, I have strong shock and I have weak shock. I have dissociation ionization happening in between the surface and the shock wave. And the dissociated compounds, like for example, dissociated oxygen can combine with the carbon in your surface that will also ablate your material. And then material ablation through heat alone, like when your material reaches a certain temperature, something called ablation temperature, it ablates, right? And there's boundary layer transition, and behind the wake, we have continuum breakdown. So all in all, this is an example of multiphysics, and like there are a lot of length scale also involved. So And also, if we look at my vehicle is going through all regimes. So it starts with rarefied regime, goes through slip flow, and then it comes to continuum regime. So I can use my CFD solvers to some extent here up to a certain portion of slip flow. But if I go beyond that, I need to use something called particle solver, which is DSMC. So DSMC, it numerically converges to Boltzmann equation. And Navier-Stokes equation also, if you try to put an equilibrium condition, in Boltzmann equation, if you put an equilibrium condition, it would give you Navier-Stokes. So yeah, DSMC is a particle-based method. We basically simulate the particles, impart some position and velocity, and based on the condition, the particle would move, and it would collide with itself, and it would collide with the surface, and producing the macroscopic flow quantities. Okay. So it is based on the Monte Carlo method, and it is not exactly solving the Boltzmann equation like solving the equation, but try to mimic the physics, right? So it typically works by like defining a grid, and then based on the DSMC requirement, my computational cell and time step has to be within the molecular range. It should not be bigger than the molecular scale of the flow conditions. And then we basically try to simulate the particles. And if we put a surface in its path, it would align based on the gas surface interaction models. And you, for example, in this particular, you could see the formation of shock wave around that blunt body. And yeah, it can handle non-equilibrium flows. Yeah, of course, like simulating real number of particles is not possible. So we assume something like a particle weight. One simulated particle is equal to certain number of real particles. Thereby, like the point is to reduce the computational effort, but still the physics is the same. And so what I did is look at the multiphysics aspect. So we have a flow domain. Solving the flow domain, I get the heat flux. And the heat, because of the heat flux, my material gets heated up, which will be solved using a thermal response solver. So in my PhD, I developed like a 2D axisymmetric thermal response solver. If I in a typical ablating material, you have a lot of thermochemical process going on. For example, if I look at the cross section of it, the virgin material is something that has not gone through heat decomposition. And the pyrolysis zone, like heat enters from the exposed surface, and this is the region of active decomposition called pyrolysis zone, and it is accompanied with production of pyrogas. This gas, perspire through the porous char layer, which is like a carbon layer, and then it forms a layer of thin, protection layer kind between the hot shock and the surface, which further attenuates the heat flux impinging on the surface. And also we have, beyond a certain temperature, ablation temperature, you have material ablation, and you have a mechanical erosion, and the radiation flux coming from the ionized gas particles inside the shock wave. And that's, again, like a lot of complex process going on. So what happens is, at the interface with all these complexities, I need to couple my flow and thermal, which is like ongoing problem, like people try to include different level of complexities. And so, yeah, so basically try to capture the gas surface interaction effect. So this is like a typical, this is like a DSMC flow domain and thermal domain. So these are flow parameters and thermal parameters. This is the material I chose, this I've got. And I mean, this is like typical computational parameter stuff. And like we begin with our trajectory. So this is my trajectory I used. And then I chose points between like 2 kilometers apart. And then the corresponding velocity, temperature of that altitude, and the number density are all known from the standard atmosphere data. And this velocity data is something that I get from the trajectory. And so when I try to couple, I need the heat flux data at a given altitude. Of course, I know by solving the flow, I know the heat flux. But I don't know what would be the heat flux in the next trajectory point, like if my vehicle is entering. So if I don't know, I cannot do the analysis. So a simple analysis to assume the heat flux is constant between two trajectory points, right? Thereby we do the analysis by assuming the heat flux varies constant, piecewise constant between two trajectory points. But the problem is the ablating pyrolysis process is nonlinear and it leads to a lot of instabilities in the numerical flow. It's over. So we do something called iterative process. Basically, between two altitude, we iterate until convergence. Then we move to the next iteration. Here you can see by using non-iterative, after a certain point, I get oscillatory behavior and it diverges. And with iteration, I get converged solution. But problem is, I try to couple DSMC in iterations, which means like huge computation, and I cannot do like multiple iterations of it, right? So I stopped kind of at that point, and I stopped saying, okay, this is enough for my PhD. So, so this is like if I stop at a typical altitude and look at look at my flow and what happens inside the material. So this is how it would look. I have a non-equilibrium flow feed outside, and the cross section of the TPS thermal protection system would look, the heat is entering this way. So yeah, I mean, like from what I just told right now, if you remember, I chose two altitude like 2 kilometer apart, right? So how do I choose my global time step? Because my flow is typically happening in like a molecular level time scale, molecular scale, and my thermal heat conduction is happening in like the system scale. So the difference is something like 10 to the power 9. And even in heat conduction, I have, if I just consider pure heat conduction without ablation, I get my time step is nothing but the Fourier number. But if I consider ablation and pyrolysis, the time step is dictated by the mass flow rate of pyrolysis gas and the ablation rate. So this dictates my del T, which is very slow, and that is a problem that I want to look. And also to quantify the criteria, like how much iterations I need to get a converged solution. That is also I'm looking. And also to converge, I don't want to execute my flow simulation again and again. Instead, if I have a sophisticated boundary model, I can just use that model to come to a converged solution. And once I reach a converged altitude, then I use my flow solver to again proceed in time. So we have something called a blowing correlation model in continuum regime, which says if a certain mass flow rate of gas comes to the surface, it sort of reduces the heat flux that is going into the material. And that reduction is given by omega, which is based on continuum. I kind of, out of curiosity, try to expand it to rarefied, and it looks complicated like that. And this is something I'm actively looking. And also I want to quantify the rate of ablation. For example, if I'm looking at a targeted reentry, for example, if atomic oxygen impart hit a surface, it can scatter, and also it can like erode the surface. How do I quantify it in a macroscopic sense, right? So that is also something I'm interested in looking, which will be in the future work. So with that, I guess the theme one, we looked at what is VLEO and advantage and challenges, and the need for better gas surface interaction model. And if we try to re-enter, which is like a multi-physics aspect, need for more sophisticated interface models when I try to couple multi-physics. So this is like a big picture of what is happening and what I did. And with that, I guess I finish my talk. Thank you.
Hello. Okay, thank you, Ahilan, for your talk. As you know, we were facing technical problems and we have started 15 minutes late. So sadly, we have just 5 minutes for questions. Who wants to start? Okay, Mario.
Okay, well, Ahilan, tremendously interesting talk. Thank you. I really like what you are doing I'm wondering about sputtering. When you have the molecular dynamic models, I assume that there will be some energy levels, probably comparable to the bond energy levels between the molecules or whatever, where you will start taking out material from the substrate. Maybe this doesn't happen at orbital energies at 7 kilometers per second. But this is something that could be interesting for electric propulsion because we do have that problem. Is this something that could be tackled with this approach? Or would it need a strong modification? Or
Yes. So I'm aware of certain DSMC simulations that has something like ablation model, which says if certain number of particles hit, certain energy is given, and which leads to an ablation, like in a macroscopic sense. But that particular interaction, how much energy is given and how much particle is extracted from it, that could be looked in from a molecular perspective, yes, and possibly try to build a model that can be, fit in this framework. Even in this, for example, we could see the formation of O2, like in the surface, in among 20,000 simulation, like 4%. 4% of the scattered were O2. And also when I tried to do long-term exposure, that also erodes some of the surface out of it.
Right, so one of the oxygens that is on the surface and
Yes,
the incoming one, they merge? And
yes, like the oxygen in silica and like the
or the
oxygen
one
in silica,
Okay, cool.
Yeah.
Thank
So
you.
that's-
Thank you very much.
Any other question?
Thank you very much for your talk.
Thank you.
It was really interesting. My question is about the molecular dynamic simulation. And what I'm thinking is that we've got kinetic energy together with thermal energy to assess the whole impact of the atom, oxygen atom. So once we have the collision, and then we evaluate the trajectory of the atom after the collision, and the magnitude of that velocity. So the difference means, I mean, mv2, the kinetic difference means the energy transfer to the substrate.
Surface, yes.
So in that sense, for the subsequent collision, you have a heat contour or a heat exchange, a temperature exchange.
Yes.
That will affect the
so
next
if
impact.
I understand your question right, because of the energy impartition to the surface, it gets
I'm
heated
saying
up.
that the temperature of the substrate
Yeah,
is not constant.
sorry,
It's a function of position and time.
I understand. I forgot to mention that for scattering simulation, we fix our, so if we look at this, the whole thickness is separated into 3 sections. The bottom section is typically frozen because there will be, when we heat up or like when the energy builds up, there will be bulk motion. So we need structural stability. And in between, we keep Langevin thermostat, which try to keep the temperature at the desired level. For example, as you said, when high energy particle incident, because of which my substrate temperature goes high, and this would act something like a damper. So thereby keeping the surface temperature like constant. And also, these are 20,000 independent simulation. So one simulation is happening at a given instance. And the next simulation is again starting in a fresh material, which is at the same
Yeah, I
temperature.
see. So I mean, is this temperature transfer, this energy transfer, transitioning into a damper model for the molecular dynamic simulation? Has it been simulated correctly? I mean, using all the, what is the underlying method of that, for simulating the transitioning the energy flux or temperature to damper? Because there is a model that transfers or that models temperature based on, or damper based on energy.
Do you mean something like accommodation coefficient that says how much of the energy will be given to the surface when an interaction happens?
I mean that for damper, because damper is like a geometrical variable, and temperature is also a geometrical variable.
Okay.
Is there any correct or known mapping between temperature and this damper?
I didn't exactly understand what you mean by damper.
Because you just mentioned that there is a damper
Oh,
like model
you mean
for
this region, which
capturing the effect of this
so like-
temperature distribution.
maybe the right word would be something like a sink. Sorry. So yeah, so the whole point of this layer is it acts like a sink to keep my temperature of the substrate at the desired condition that I want. For example, when we try to fix the simulations, there were initial simulations that shows the temperature shooting up really high because the energy is too much. So then what happens, like basically the structure disintegrates. So then you try to choose by your sensitivity study how much thickness I would keep so my structure is stable. At the same time, the surface temperature. Even here, the surface temperature would not be exactly that because it's like the statistical average of the kinetic energy. So it would be like plus 20 Kelvin, something like that.
Okay, I understand. Thank you.
Okay. I think we can probably, there's no more questions, so we can close the session here. So thank you very much, Ahilan, for your talk. Ahilan is, your office is 71H20? 20. So if you want to visit him, discuss further in detail, his doors are open.
Yeah.
And nothing else. Thank you very much. Okay.
Thanks. And thank you for your patience. Yeah.